Hey, Dr. Clark here, and in this preview video, we're going to take a look at section 3.1, linear models. Let's take a look. So in this section, we're looking at a variety of models of phenomena that can be modeled by linear equations. So now why are we starting with linear equations? Well, we've done some modeling already, but we're going to focus in on linear models because, well, actually they're pretty easy to solve, or at least can be solved in some situations. And they're actually pretty useful. There's a lot of scenarios where linear models are good and model reality really well. And linear models oftentimes form the foundation of more complicated nonlinear models. So every good nonlinear model has a linear model on the foundation, which is then modified and adapted above. So linear models are actually just really good, and that's why we got to start with them. Now, in the book, if you do some reading, there's a lot of really good examples in there. We're going to do a bunch of them in class, but not necessarily every single one. So if you want to learn some more modeling and see a bunch more scenarios, do read in the book, and you'll see a bunch more. And then just to kind of get your your frame of mind here, what does a linear model actually look like? So we're really going to look at first and second order here. So a first order linear model, well, it's really just a linear differential equation. First order means first derivative only, and then a of t times y plus b of t. So that's a first order linear model. You'll notice the y is by itself. It's not multiplied by anything except for a function of t. It's not y squared. It's not square root of y. It's not 1 over y, right? It's just the y prime by itself, and then the y multiplied by a t function and possibly added to another t function. So this is oftentimes called the forcing function, and this is relating to the example. So a good example of this would be, for example, if we set a to be just a constant and b to be 0, we get y prime equal ay. That would be like exponential growth or exponential decay. So that's a really simple first order linear model that we've seen several times. Now, second order, that means we've got a second derivative, and then we put everything else on the right-hand side. But again, the y prime and the y are by themselves, except possibly multiplied by a function of t, the independent variable, and b of t for the y, and then another third possible forcing function, c of t. A good example of this would be anything coming from Newton's second law, F equals ma. So you'll notice in F equals ma, a stands for acceleration. That's the second derivative of position. So a lot of times that y double prime is like a second derivative, and then everything else that's telling you how that acceleration comes from is on the other side. So like a nice example is like a spring on a mass, or a mass on a spring bouncing up and down, or a pendulum going back and forth. You can write second order linear models for those kind of phenomenon. But because they have to do with acceleration of this mass on a spring, for example, that's where the y double prime comes in, and then the other terms are given meaning in the situation. Okay, so that's just a quick intro. It's basically what does a linear differential equation look like, first and second order. In class, we're going to jump in and hit up a bunch of examples so you see the modeling in action, and I'll see you there.